Yes, sir.
Yeah, please start.
Yes, sir. Okay, guys. So sorry for the disturbance. So we have started our discussion, and we were looking at this question: the fatigue strength for an non-ferrous
Yes, sir.
material.
Yeah, please start. Yes.
So we have just given for the reminder that I have told you a small revision what is the meaning of fatigue strength and how we determine the fatigue strength, right? So fatigue strength is nothing but the maximum value of the bending stress a material can withstand when it is about to complete 1 million revolutions. That means below that stress, it will make infinite number of cycles. Above that, it will not make 1 million revolutions, and we won't say that that is a life of a fatigue life of a component. We say fatigue life of a component. At least that component should make 1 million revolutions, right? And for non-ferrous material, the fatigue life is defined as when it completes 10 to the power 7 cycles, right? So these are the things we have seen. Now again, one more question is there that is belonging to dynamic loading. For the plate with an elliptical hole is being subjected to tensile stress, as you can see, where the tensile stress is what sigma, and they are asking what is the maximum tensile stress at a point P. At a point P, what is the maximum tensile stress? They are asking. Okay, so now for solving this particular problem, for question number 38, here you observe whenever this type of condition is given, right? Whenever any hole is there and there is a something called, you know, for any hole, we have uh, stress at that near to the hole, very high value of the stress is there, right? The localized stress will be very high. And how we define that localized stress? By using the theoretical stress concentration factor, right? So here any hole is there. Let's example, for example, we have a plate. It is being subjected to sigma. Let's say there is a elliptical hole. Whenever the stress is acting or the load is acting perpendicular to the major axis, there we say due at the location of nearer to the hole, nearer to the elliptical hole, the maximum stress will be kt time nominal stress. The nominal stress that is being given as sigma. But what is the kt formula? kt formula we know that 1 plus 2. Now, if major axis is A and the minor axis, let's say for example, is B, semi major axis is A and semi minor axis is B, then we when the load is acting perpendicular to the semi major axis, then we define 2A by B like this. Put a note and note down. Whenever we have the hole and where the elliptical hole is something like this. Now, when the load is acting perpendicular to for example, this is A, this is B. Now the load is acting perpendicular to semi minor axis. Then what is the KT value? Note down the KT value. 1 plus 2. What will be the KT value? When the load is acting perpendicular to the minor axis. When the load is acting perpendicular to the minor axis, so it will be 2B by A. Sorry, 2 into B by A. 2 into B by A. That's the only change will be there. But here the load is acting perpendicular to the semi major axis, then A will be coming in numerator and the semi minor axis will be coming in denominator. Here the load is acting perpendicular to the semi major minor axis, so B will be coming in numerator and the semi major axis will be coming in the denominators. Right? So here, while you look at this scenario, A is what greater than B. There is no doubt. A is what semi major axis of elliptical hole, and B is nothing but semi minor axis of elliptical holes. So what you are understanding, KT will be more than 3. KT is coming out to be more than 3. If A will be, let's say, 20, B is 10, then automatically you will be getting more than 3 value. then how much of sigma maximum at a point P? It will be more than 3 times of sigma. Yes or no, guys? Check it out. If kt will be more than 3, if kt will be more than 3, and we know that sigma is what? Sigma maximum is kt times of sigma. Then automatically we can say that if sigma maximum, for example, kt is coming out to be 4.5, then 4.5 to sigma, then can we say it is more than 3 sigma? Yes, that is what they are asking. More than 3 sigma. If it is a circular hole, if a is equal to b, just like if this particular value it has, let's say a circular hole where a is equal to b, then kt will be exactly equal to 3. Kt exactly will be equal to what? 3, my dear, no doubt. So what is the maximum value of the kt? What could be the maximum value of the kt for a circular hole? 3. For a circular hole, I'm talking about for the circular hole. So this is also one of the important question. Now try to solve this particular question. Question number 41. A rod of the length L, the rod of the length L and having a cross-sectional area A has a modulus of elasticity A and the coefficient of thermal expansion alpha. One end of the rod is fixed. One end of the rod is fixed. And what about the other end? Other end is free. Other end is free. If the temperature of the rod is increased by delta T, then what about the stress and what about the strain? They are asking. What about the stress? What about the strain? See, when it is free to expand, this case is belonging to case number 1. In thermal stress, we have different cases. So generally, when you follow IGC notes, we have case number 1, that is free expansion case. In case of free expansion, when we increase the temperature and when there is no resistance offered by the support, then why the material will offer some kind of resistive force when it is free to expand? See, material wants to expand because every material will have coefficient of thermal expansion alpha. That is a property of the material. When you change the temperature, then because of the alpha, it will try to contract or it will try to expand. That is a property that you cannot stop. When the material wants to expand or when you reduce the temperature, material wants to contract, you are not going against the material behavior, you are supporting the material behavior. Then why the material will resist? And there is no resistance, there is no stress, right? So there will not be any stress developed in the rod will be zero. Whatever the stress will be there, that is being developed in the rod, will be zero. But what about the strain? Definitely it is try to expanding, so we know that there is a thermal strain will be developed. Of course, there will not be any mechanical strain, but here thermal strain will be developed, that is alpha into delta T. So B option is correct. No. If there is some kind of support, either flexible support or rigid support, then we would have been said that there will be not a free expansion. There will be certain restriction will happen. But here there is no restriction as it is free to expand. As it is free to expand. And what is the expansion? Thermal expansion, alpha into delta T into L. How to determine the thermal strain? It will be alpha into delta T into L divided by, that is a change in the length. Whatever the change in the length will be there, let me write to be delta thermal by total length. So alpha into delta T. That is same in X, Y and Z directions. In all X and Y, Z directions, it will be same. Strain developed in X, Y, Z direction will be same alpha delta T. Alpha delta T. and whatever the stress developed in x, y, z directions, all will be zero. All will be zero. To be precise, stress developed in x, y, and z directions, all will be zero. And whatever the strain will be there, that is equal to epsilon x, epsilon y, epsilon z. If you just consider this to be x, this to be y, this to be z. So make a note of it. Okay, moving on to the next question. The figure shows an aluminum rod of 25 mm square. It is loaded at 4 points KLMN, assuming the E value for the material to be 67. Uh, all the three cases. See, let me explain. So, case number one is a free expansion case. Very quickly note down. Case number two, completely restricted case. Completely restricted case. Completely restricted case means here when you just see the completely restricted case, a bar is fixed at both the ends. Now, when you change the temperature of having length L, cross sectional area, you can say mm, area to be A, where D is the diameter. So, in this case, my different, when you increase the temperature, first of all, it will try to expand freely, but the support will offer some kind of support reaction R. So, because of that, total deformations, total deformation to be zero. In that total deformation, we know that mechanical deformation will be there, thermal deformation will be there, and combination of these two will be the zero, right? Again, mechanical deformation we can write R L divided by A, but that is minus. Why minus? Because there is a compressive load which are acting at any section. When you just see, there is a minus R load is acting. Because of that, mechanical deformation will be like that. And thermal deformation is what? Alpha into delta T into L, that is zero. So when you calculate R, you will be getting alpha into delta T into A into E. What about thermal stress? You will be getting alpha into delta T into E. Note down. That is a compressive. Those who are not able to understand, they can understand by principle of superposition. How? You can apply principle of superposition something like this. You assume that there is a at the free end there, at the right side there is a no support. You remove the support, and now you increase the temperature. What will happen? It will try to expand. In the second step, you put the whatever the your bar might be expanded like this. Now you keep it the support. When you keep the support, there will be certain reaction force. What the reaction force will say, you just go back and it will try to offer some kind of mechanical deformations, and that is equal to RL divided by A with the negative sign. Right. So when you combine these two cases, you will get something like this. Here it is alpha into delta T into L. Here because of this there is a mechanical deformation, and it is a completely restricted case. That means how much amount of thermal deformation will happen, the same amount of mechanical deformation gonna happen, right? Make a note of it. So this is the case number 2. We have another case that we already talked in one of the ISRO session, that previous year question session, that when we have a certain gap, right? That is the case number 3, partially restricted case. Now, whatever the stress will be developed, that is in the x direction. Here in the y and z direction, if there is a no support, then y and z direction stress will be zero. If there is a no support in the y and z directions, if there is a no support, rigid support in the y and z direction, it will be zero, right? But whatever the thermal deformation will happen here, the thermal deformation in x direction, or thermal strain in x direction will be what? See, the total deformation is zero, but the thermal strain will be there in x direction, that is alpha into delta t. All of your understanding? Yes. Now, can we move to the next question? So, today we learned something good thing about the stress and strain diagram, and then we learned about the endurance strength. You know, so now we will talk about the case number three. Now, down partially restricted case. That is the case number three, partially restricted case. And remember, my dear friend, here we talked about the, let's say, this we have considered a circular bar of having diameter d, for example. Here in this scenario, the total deformation is zero in x direction. Remember, it is zero in x direction, not in y and z directions. We have certain deformations in y and z directions, right? We will have certain deformations. We will have a total strain in y and z directions. That is not equal to zero because we will have a change in diameter. That is not equal to zero. Change in length is zero. Whatever the change in length is there, that is zero. But change in diameter will happen because of the Poisson ratio. Because of Poisson ratio, right? Here, partially restricted case, no doubt. A material is there, and we have a support at a distance lambda. It is having a length L. For example, it is having a length. Now, lambda is what? The expansion which is being permitted. The expansion being permitted. Now, this expansion can be anything. This expansion can be anything. If I give the example here, if I talk about the example, I can give certain example like this also. A bar is connected to a spring. So whatever the deformation will happen in the spring, whatever the deformation will happen, that is Rs divided by K, that is acting like a lambda. So if the question will be coming, bar is connected to spring, do not confuse. It is the same case, partially restricted case where the temperature got changed. Here also temperature got changed. So here what will happen? Whatever the total deformation in earlier case, we are writing to be zero, but here it will be lambda. Now you know that total deformation means what? We have mechanical deformation, we have thermal deformations. Mechanical deformation, change in the length because of the mechanical forces will be minus R L divided by A. The reaction force offered by this. Thermal deformation will be alpha into delta T into L. So R into L divided by A will be it will be alpha into delta T into L. Alpha into delta T into L. minus lambda into AE by L. If I just see R, if I just calculate R, so R will be alpha into delta T into L minus lambda into AE by L. Now when you calculate thermal stress, that is R divided by A, so that is going to be alpha into delta T into L minus lambda into E divided by L. That is compressive. For this, you need to understand alpha into delta T into L should be more than lambda. Then only thermal stress will be not equal to 0. Otherwise, simply straight away it will be 0. If alpha into delta T into L is less than lambda, then thermal stress will be 0. So that is all possibility of the cases that they can ask. Note down. So here moving on to the next question. Here the figure shows aluminum rod of let me make the figure once again in the here we have the member where it is KLMN, where the load is acting 50 Newton. Here the load is acting 100 Newton. Here the load is acting 250 Newton. Here the load is acting 200 Newton. 500, 400. Here we have 500. Here we have 400 mm. Here we have 1700 mm. Now you understand what I'm talking about. So they are asking my different the total change in the length because of the loading condition what they have given. So now you just try to calculate. Let us consider three segment KL, LM, and MN. Right. So very first of all, what is the load which are acting in KL member? Whenever you are calculating load, either you have to see left side or right side. Do not see both the sides at a time. Either you calculate like this or you calculate from right side. So left side we find that it is only the easy thing because only one load is acting 100 Newton, that is plus, because load is going away from the cross section. What is the load which are acting in LM at any section? What is the load which are acting 100 that is going, I'm calculating from the left hand side, so 100 that is going from towards the left side, but minus 250. Why minus 250? Because it is coming towards the cross sections. What is the load which are acting in MN section? Either from the left side or from the right side. From the right side it is plus 50 Newton, or you are very much interested, no sir, I just want to calculate from the left side only. So plus 100 minus 250 minus 200. Once again you gonna get the same answer. Here the 250 will be what? Yes, that is correct. So 100 that is going towards the left side, minus 250 plus 200, right? So that is plus 50 Newton. So now you have to calculate total change in the length, that is equal to change in the length of KL, change in the length of MN, change in the length of LM. What is the KL change in the length? PKL, LKL, area KL, EKL. In short, I want to say the deformation is what? PL divided by A. PL divided by A. So now when you calculate for PM, PMN, LMN, AMN, EMN. Same thing, PL divided by A for LM. Put that value, get the answer. Put those values, you will get the answer. delta total will be PKL. PKL is what? 100. Length for KL is what? 500. Area for the KL, area for all the sections they have given clearly in the problem, 25 mm square. And what is the Young's modulus for elasticity? 67 gigapascal. So 67 into 1000 megapascal plus PMN. PMN is what? Minus 150. L11 will be 9. That is 800. See, I have no. I'm calculating for LM. This is for LM, right? A into E plus what is the value in MN? What is the value in MN? That is plus 50. Length will be what about the length? Length will be 400. Length will be 400, and then area will be 25 into 67 into 1000. So when you combine together, when you just combine together, what you will be getting? The total change in the length would be what? The total change in the length would be what? Approximately minus 30 into 1000 mm, or you can also write minus 30 microns. In terms of meter, you can write like this, because 1 mm will be 10 to the power minus 3 meter, right? No, just wait. It will be 30 by 1000. 0.03 you are getting as. See, negative sign means, what is the meaning of negative? That means whole bar will be shifted towards the left side. If we are supposed to get positive, that means that is we are gonna get positive in the positive x directions. But here we are getting negative means what? The whole beam, whole bar will be shifted to the left side. All of you are getting the same answer. Check it out. Minus 30. All of you are getting minus 30. Yes. Hello. Are you getting minus 30? Check it out, guys. All of you. Are you getting the same answer or what? Correct. Moving on to the next question. This question is very, very important. Again, repeated from the gate examinations. They are giving the simply supported beam. They are giving the simply supported beam, which is being supported over the length of L. And we are moving from here x equal to 0 to x equal to L. So what you are understanding that when you plot the sine curve, right? Whatever the load they have given, the load is given as sine pi x by L. Sine x is 0, that is being 0. Sine pi, that is also 0. What is the sine pi by 2? Or we can say at a distance L by 2. What is the length at a distance L by 2? What is the distribution of the load? That is sine pi by 2. That is we are going to get 1. So you want to get the sine curve like this. The uniformly distributed load is given in the form of sine curve like this, right? Where it is W Newton per meter. Very first of all, we have to calculate simply supported beam. It is a symmetrical loading case. Then what is the reaction force? What is the reaction force? RA and RB. If this is A, this is B, that is gonna same. The total load divided by 2. When it is a symmetrical loaded case, then RA and RB for a simply supported beam will be same. Will be same, and that is equal to total load divided by 2. How to calculate total load? Total load, just I told you, we supposed to be, let's say we have uniformly distributed load. Then how we calculate? W into dx from 0 to L. So we used to write W into L. But here we have to perform integration sine pi x by L into dx. That's it. From 0 to L. So now when you perform total load, 0 to L sine pi x by L into dx. What is the sine pi x by L? Minus cos pi x by L divided by pi by L, because we have to differentiate and we have to write in denominator. Minus cos pi minus cos 0 divided by pi by L. So now when you put the value, you will be getting what? 2L divided by pi Newton total load. But they are asking what is the reaction force Ra and Rb. That is equal to 2L divided by pi by 2 L by pi vertically upwards. That is Newton. Then what should be the correct answer? The correct answer would be L by pi. Now, the next question again we have discussed, guys, and I told you very significantly, right? Whenever any residual stresses will be there, right, or anything we want to relieve from the residual stresses, or let's say you have compressive residual stresses in the weld joints, then what will happen? It will increase the fatigue strength. The reason I have given you, right? Because when you plot variable stress versus mean stress graph, you will get something like this, like this. Soderbergh, Gerber, and Goodman plot you will get for a tensile load. But when you load the material in the negative x directions, right? When you apply the mean compressive stress, you won't find anything changes which are happening in the amplitude in the endurance limit. In endurance limit, it will not change. But when you keep on applying the tensile load, it will be start decreasing. See that? It will be start decreasing. But when you just apply the compressive load, the endurance strength of a component will not reduce because we have the graph, horizontal graph like this. So C will be correct. Again, this type of problem I told you, whenever we have a structural problem, whenever we have any structural problem, simply transfer the load where they are asking. They are asking what? They are asking what should be the displacement at a particular point A. That means they are very much interested in junction point at A. Transfer the load. Whenever you want to transfer the load from any point to any other point, simply what you have to do, you have to introduce two equal and opposite load, P like this. P like this. Now this P will be acting like a load. This is a simply supported, this is a cantilever beam where it is being subjected to load P, but this P and this P, this P and this P will cause a movement in the anticlockwise direction. Something like P into 2L minus X. I told you how to transfer the load. If still you have doubt, then again go back to the lectures and see that. Now they are asking what should be the displacement. What should be the net displacement at a point A? Then what should be the answer? See, there is a load which are acting in the downward directions, and there is a movement which are acting P into 2L minus X. So now we can apply principle of superposition. First, there will be deflection because of this P, and we know that deflection formula P into 2L whole cube divided by 3EI, because the length is not L, the length is 2L. You have to remember that. You have to remember that. And we also know that here, because of the movement, it will be deflected in the upward directions, and that deflection is delta 2, P into 2L minus X. And we know that this delta 2, what is that value? ML square divided by 2EI. Sorry. Yes, correct. Here we can write m as p into 2l minus x. Length will be 2l whole square divided by 2ei. So what is the deflection one? 8pl cube divided by 3ei. And deflection 2 will be p into 2l minus x 4l square divided by 2ei. The net displacement has to be 0. That means delta 1 equal to delta 2. So that no deflection will be there. So 8pl cube divided by 3i, that is p into 2l minus x 2l square divided by ei. E this will cancel out, p will cancel out. We can write 8 by 3 into l, that is 2l minus x into 2l square. 8 by 3 into l cube. So that is 4l cube minus 2xl square. So 2xl square, that is 4l cube minus 8l cube divided by 3. So 2xl square 4l cube divided by 3. So here we can write it as further. X will be 2l divided by 3. That means x will be 0.67 times of l. When x will be this distance will be 2 by 3 times of l, then we can say the displacement at a will be 0, because we are loading in such a way that the displacement at a has to be 0. Make a note of it. If you just follow other than this method, let's say not you are not following any principle of superposition method, then you may end up getting trouble in examination, because if you try to follow double integration method or any other method, you will be in a trouble because you might be doing some silly mistake. Remember, the length is not l, length is 2l. That's why we are adding here 2l. Yeah, that's why we are adding here 2l. Actual formula is what? ml square divided by 2ei, l effective. When the length is l, but when the length is 2l, then it has to be replaced by 2l. Okay. Moving on to this particular questions. Again, very simple question from torsional loading. A torque T is applied at the ends, right? The shear modulus of the material is Z. That means for this material also G, for this also Z. The expression for the diameter D to produce an angular twist theta at the free end. That means A, B, C. So they are saying that if you load the material like this, we are applying the twisting moment like this T. Here the diameter is 2D. Here we have the diameter D. That let A, B, C. They are saying theta C total. That is theta C with respect to A. That is theta. Whenever theta C with respect to A is there, then we can write theta C with respect to B plus theta B with respect to A. That is equal to theta BC plus theta AB. That is equal to theta. Theta BC is what? Theta BC is what? TL divided by GJ for BC. So here we can write T is same for both AB and BC. If you just follow any section or twisting moment diagram, it will be same. It will be T only. Yes. So here we can write here a T. What is the length of the BC member? Length will be L. Here they have given the length to be L. Here the length is given as 2L. Sorry, L by 2. Let's check it out. Here the length is given as L by 2. So T into L. For BC I am writing G into J. For BC, what is the J? J for BC will be what? Pi d power 4 by 32, and J for AB section will be what? Pi 2 d power 4 divided by 32, right? So now GJ pi d power 4 by 32 plus T into L by 2. I'm writing for AB section. G will be same for both the AB and BC section. Pi 2D to the power 4 divided by 32. That is equal to theta. That they have given as theta. So when you just combine together, you will be getting here 33 TL divided by G pi d power 4, that is equal to theta. So they are asking diameter, so diameter will be 33 T into L divided by G pi into theta to the power 1 upon 4. This will be the answer. So 33 means B will be correct. Right? Because here it will be 32, this will all cancel out. So this will be 32 T into L divided by pi G d power 4, plus here it will be 32 T L divided by pi G d power 4. When you add together, you will get 33 T L pi G d power 4. So this is your what you have the twisting moment diagram. That is a when you follow, that is negative, because if you follow the sign convention, the double arrow towards like this at any section, it will be minus t. So when you just follow the right hand thumb rule, so when you rotate your fourth finger in the same sense of twisting moment, you will find your thumb is going towards the negative x directions. That is what you can write twisting moment diagram. So they can ask in ISRO what should be the twisting moment diagram also. So please note down like this. They can give the question. Here it will be t. Here it will be 2t. And they may ask what will be the twisting moment diagram by giving the 4 options. Okay. So this question I will do it at the end. Before that, we will try to do this theories of failure questions. Now, in this theories of failure question, this particular graph is a failure graph. This basically curve what they are giving, that is a safety region. And we generally plot this graph for factor of safety equal to 1. Every theories of failure, they used to give some safety region. That means your point should not go beyond this point. Let's say point P is lying here. When you design and when you load the component P in such a way that sigma 1 and 2 you will find, and you are getting sigma 1 and 2 coordinates something like this, sigma 2 here, sigma 1 like this. That means that material is already failed by some theories of failure. That is the meaning of that graphical representation of the sigma 1 and sigma 2. The first representation what they have given here, we will see the other representation also. See here, what is this particular representation? This particular representation is for maximum normal stress criteria. C will go with the M. So here we have two options. What about the maximum distortion energy theory? Maximum distortion energy theory, you will find ellipse. You will find the graph as ellipse, right? Because when you do the simplification of that equation, you will find that equation is belonging to ellipse equation, elliptical equations. So that is nothing but maximum distortion energy theory. So here B will go with the L. So B will be correct. B will be correct. No doubt. Here the B will be correct. Now, to explain, sir, how we plot the graph, to explain this particular scenario, let me explain you by giving one example of maximum normal stress theory. Right? What is the maximum normal stress theory they are saying? When you load the material in such a way that, suppose you are loading the material where mod sigma 1 is greater than mod sigma 2 greater than mod sigma 3, then if mod sigma 1 is more than yield stress, if I talk about ductile material, if it is more than yield strength of a component, then we say the material is failed. That is the maximum normal stress theory. We also say Rankine's theory. How to plot that? Sigma 1 and sigma 2. See very carefully. If mod sigma 1, see, and remember that whatever the plot we are doing for 2D. that means sigma 3 will automatically 0 here, right? So if mod sigma 1 is greater than mod sigma 2, then mod sigma 1 will decide the failure criteria, that is equal to sigma yt. Now when you remove the mod, you will get the two things. One will be plus sigma yt, other you will get minus sigma yt. So sigma, sorry, other you will get one you will get plus sigma, other you will get what, minus sigma yt, right? So now when you plot here, sigma 1 is equal to what, sigma yt somewhere here, and sigma 1 is what, minus sigma yt somewhere here. Generally for a ductile material, sigma yt is almost equal to sigma yc. Actually this is what, sigma yc only, this is sigma yc. But for a ductile material, we say sigma yt almost equal to sigma yc, right? And if mod sigma 2 is greater than mod sigma 1, in that scenario what could happen? uh, Sigma 2, mod sigma 2 will decide the failure, then sigma 2 will be plus sigma yt, sigma 2 will be minus sigma yt. So you will get another plot like this, and that's how you get what we call symmetrical square section. Symmetrical square section. Safety region, whatever you will plot, you will get symmetrical square section for what we call ductile material. Of course, this theories of failure is not very much suited to ductile material, but it is very much suited to brittle material. Now you will ask, what will be the graph for brittle material, right? So here for brittle material, remember that sigma yc is more than, sorry, for brittle material there will not be any yielding. So whatever the ultimate stress in compression will be much higher than ultimate stress in tensile, right? So in that case, you will get the graph something like this, something kind of unsymmetrical one. Here we have sigma 2, here we have sigma 1. You will get the graph unsymmetrical square section. Unsymmetrical square you will get for brittle material. Because this theories of failure is very much suited to brittle material, maximum normal stress theory. That's why it is very important to know safety region for uh, brittle material. In all the cases, in all the textbook, you will find they used to give for ductile material, that is symmetrical section, right? But generally it is not a symmetrical for brittle material. Again you will plot for this maximum normal stress theory, maximum shear stress theory, we also say trespass theory. Very easily you can plot. I'm not plotting here because if you want to have full detailing of that, then you can follow IGC notes, right? So for this, answer will be B. The next particular question is belonging to welded joints, here riveted joints, are rectangular plates which is joined by 4 identical rivets. The shear load on the worst loaded rivets will be what? So here, for the worst loaded case, for the worst loaded rivets, we have to find what should be the shear load. Again, you know that whenever any riveted joints will be there, any riveted joints you will take, it will be subjected to two kinds of shear load. One is a primary, other is secondary shear load, right? At the centroid, we have to transfer the load. So what will happen? Introduce two loads, P and P. This bottom P will give me, if I plot separately, this is a one rivet, second rivet, third rivet, and fourth rivet. This is the P, and there is a twisting moment will also be acting, right? Because when you transfer, there will be twisting moment. Why not bending moment? Why twisting moment? Because whatever the moment is acting, that is a parallel to the cross-sectional plane. Whatever the plane of bending is there, plane of whatever the moment is acting. The plane of moment is what? It is in the same plane in which cross-sectional area has been there of a rivets, right? So that's why we are calling this to be twisting moment. Now, what will be the scenario? This, whatever the shear load which are acting P, because of that there will be primary shear force will be developed in each rivets. They will try to see, this is 1, 2, 3, 4. So there will be primary force which will be developed, and because of this movement there will be twisting movement will be developed. They will try to resist this particular twisting movement by the shear force. That is called secondary shear force. That is called secondary shear force, like this. The twisting moment, external twisting moment is acting in the clockwise direction, so they will try to restrict, they will try to resist this twisting moment such a way that the net moment about point O has to be 0, like this. They will offer secondary force PS2, PS1, PS3, PS4 at a radial distance R1, R2, R3, R4. Of course, in this case, R1 equal to R2 equal to R3 equal to R4. So how to calculate primary force? Primary force you can calculate P1, P2, P3, P4, that is equal to P by 4. Why P by 4? Because exactly this load is being acting at a centroid. So they will be equally distributed. Now what is the load which are acting? The load is what? 840. That 840 divided by 4. How much it will be? 210 Newton. That is the primary force we got to know. That primary force is 210 Newton. What about the secondary force? The summation of moment about O has to be 0. The summation of moment about O has to be 0. Now, when the summation of moment about O is 0, then how we can write? The summation of moment about O to be 0, then we know that secondary force into R1, secondary force into R2, because that will be acting perpendicular. Why perpendicular? Because we know that twisting moment or torsional shear stress will only be developed when the load is acting, when the shear load is acting perpendicular to the radius. Perpendicular to the radius, right? Something like this. Perpendicular to the, like this. At any point, it has to be perpendicular. Then only circumferentially it will be acting and it will produce the torsional shear stress. Plus PS3 into R3 plus PS4 into R4, that is equal to P into E. P into E is what? What is the P into E? P into E means this external movement. What is the E? E they have given as 300 mm. E they have given as 300 mm. So here they have given it as 300 mm. So what we can write? Now we also know secondary force is directly proportional to radius, right? More and more radius, more and more amount of secondary shear force will be developed, more and more amount of torsional shear stress will be developed, because torsional shear stress from the twisting, what is the twisting equation? We know that. What is the torsional equation? Tau is directly proportional to R. That means tau is what? Shear force divided by area is directly proportional to R. That means shear load is directly proportional to R. So here we can write K times of R1 square plus K times of, we can also write PS is equal to K times of R. R2 square plus K times of R3 square plus K times of R4 square, that is P into E. So what will be the K? K can be written as P into E divided by, see here R1, R2, R3, R4 all are equal. So we can write 4 times of R square. And but now we have to calculate what is the R. What is the R? Here it will be, this is the R. This is 30. This is 30. So this will be 30 into root 2. R will be what? 30 into root 2 mm. So first of all calculate K. P is what? 840 into 300 divided by 4 into 30 root 2 whole square. Now when you calculate K, when you just calculate K, how much of K value you are getting? 840 into 300 divided by 4 divided by 900 divided by 2. You will be getting 35. Multiply with that, you will be getting secondary force. Anything, PS1, PS2, PS3, you will get same. 35 into R1. R is what? 30 root 2. What is the secondary force you are getting? What is the secondary force you are getting? 35 into 30 into root 2. You will be getting 1484.924 Newton. Once you got the values of secondary force, once you got the value of primary force, now tell me the worst loaded rivets. What will be the worst loaded bolts or rivets? out of 1, 2, 3, 4, which is the worst loaded one. If you want to determine the worst load, it means where the maximum load is acting. And you know that whenever at any point two forces are acting, by the parallelogram laws, we know that the resultant force we can calculate by using this formula: pp1 square plus ps1 square plus 2 pp1 ps1 into cos theta. pp1, pp2, pp3, pp4 all are same, right? So now it depends on the theta value, right? How to calculate theta? How to calculate theta? This is the theta what we have. This is what we have theta. This is what we have theta. This is what we have theta, right? So now tell me what is the worst loaded bolts you will get out of this two, out of these four here. One, two, three, four. Tell me guys. Whatever the included angle is there, that included angle you need to be very careful. See that load, whatever the rivets 2 and 4 are there, rivets 2 and 4, they are very close to the load, right? So definitely they are the worst loaded rivets. See that? Definitely they are the worst loaded rivets. So what we can write further? And what about the angle? Now how much of angle will be there? How much of angle it will be there between included angle here? Theta here is acting what? Theta here. Here let's say here what? Theta. But here whatever the included angle is there, that is a larger one. When theta will be more and more, cos theta will be lesser and lesser, the resultant load will be lesser and lesser. So we have to remember that when theta will be more, the resultant load will be less. When theta will be less, the resultant load will be more. Understanding all of you? So 2 and 4 both are what? The worst loaded rivets. So what should be the theta value? What should be the theta value first of all? Let's say this is theta dash. This theta dash is what? 45 degree. So here it will be what? Once again, this is also what? 45 degree. So what we can write? The resultant load will be under root of 210 square plus 1485 approximately plus 2 into 210 into 1485 into cos 45. Right. So now when you calculate the resultant load, you will be getting 1640. Approximately you will be getting 1650 Newton. So what should be the right answer? No, just wait. Here, just calculate what is the resultant load, how much of you are getting. What is the resultant load? 210 square plus 1485 square plus 2 into 210 into 1485 into 0.707. Under root of that, 1640. Are you getting 1640? Check it out. Yes, how much of value you are getting? All of you? All are getting 1640. Check it out. Then what should be the resultant load? Approximately you can say 1650 Newton will be the worst loaded rivets load which are acting. Understanding all of you? The shear load is they are not asking primary shear load. They are not also asking secondary shear load. They are asking combined resultant shear load. Right. For this particular case, in this also we have three cases. Maybe I will discuss in next class all the three cases where the eccentric loading case is there. In eccentric loading case, in eccentric loading we have three possible cases, right? This is the third case. I will discuss one and two cases in our next class, right? I will tell you like what are all the forces which will be developed in all these separate cases. In this particular case, this particular rivets will be subjected to both primary as well as secondary shear load. There will not be any tensile load, there will not be any normal stress. Understanding, all of you? Is that clear? No, 1580 is not correct. 1650 should be correct. Check it out. 1650 should be correct. Right. And remember, regarding angle wise calculation, here it will be theta 2, here it will be theta, sorry, here it will be theta 1. What we have theta 2, here we have theta 4, here we have included angle theta 3. So here theta 2 equal to theta 4, that is more than theta 1, that is equal to theta 3. And sorry, here theta 2 and theta 4 are less than theta 1 and 3, right? When theta is less than that, then resultant load will be more, as cos theta will be uh, more, right? Because in case of cos, you know that as you keep on increasing the angle, cos theta value will be start decreasing, right? Remember, included angle is smaller side angle. Don't calculate like this. No, take a smaller side, whatever the smaller included angle. Take the included angle where it follows. Oh, sorry, where it follows the shortest route between these two particular lines. That means I want to say this is the primary force, this is the secondary force. So this will be the included angle, theta. Don't take this included angle, right? Otherwise, you will confuse, because here we plotted like this. You know, in case of that, you have seen that we have written 2 and 4. Uh, if I just show here, in case of this, the primary force like this, secondary force will be what? It will be like this. So whatever the angle is there, this will be the angle for 2 and 4 both. Don't calculate like this, right? That is all I want to say. So the worst loaded rivets will be 2 and 4. If you just want to name it, you can name it here. The worst loaded rivets will be, if you just give 1, 2, 4, 3. So the worst loaded rivets will be 2 and 4. It is quite clear also, because 2 and 4 are very much nearer to the 840 Newton. 1 and 3 are far away from the 840 Newton. Right? Thank you all.